Hi, in this video we will learn what is the coordinates of a vector with respect to a basis. Throughout this video I'm going to assume that vectors v1 up to vk, which will be denoted by b, is a basis for subspace S of Rn. So we fix a basis for a subspace. Then you see we know that span of curly B is going to be equal to S. Means what? Means that every vector U in S can be written as linear combinations of vectors v1 up to vn. So u is equal to c1 v1 up to ck vk. Very nice. But is this the only way we can write this vectors as linear combinations of v1 up to vk? Is there any vector in S that you can write more than one way as linear combinations of v1 up to vk? Well, let's see. If there is any other one, let's assume that there is another version. So u is this time equal to c1 tilde v1 up to ck tilde vk. Yes. And since these two are equal to u, so 1 and 2 together imply that c1 v1 up to ck vk is going to be equal to c1 tilde v1 up to ck tilde vk. Now you bring all the terms one side, so this will be c1 minus c1 tilde scalar multiplied to v1 up to ck minus ck tilde times vk equals to 0 vector. Knowing that v1, v2, v up to vk are linearly independent, so this is the second condition, that B is a set of linearly independent vectors. This implies that the only way we can write 0 as linear combinations of these vectors is that the coefficients, all the coefficients are equal to 0. So C1 minus C1 tilde is a coefficient of V1, so that needs to be equal to 0. C2 minus C2 tilde, which is coefficient of V2, needs to be equal to 0. And this goes up to CK minus CK tilde needs to be equal to 0. From here, you see that C1 needs to be equal to C1 tilde, C2 needs to be C2 tilde, and CK needs to be equal to CK tilde. And what does this say? This says that, okay, there is no other way to write vector u, which was the arbitrary vector from the subspace S, as linear combinations of v1 to vk. There's only one and only one, exactly one way to write u as linear combinations of v1 to vk. So the theorem is proved now based on the information given above. For every vector u in S, there are scalars, unique scalars, C1, C2 up to CK. These are scalars, not vectors, such that U is linear combinations of V1 up to vk with the coefficient c1 up to ck. So this is unique. Having unique set of numbers tells us that, well, put a name for those ones, that those can be important set of numbers. And yes, we have a name for that's called the coordinates of u with respect to that basis. So the scalars is c1 up to ck are called the coordinates of u with respect to basis curly b. And if we put these numbers in a column vector c1 c2 up to ck, this column is denoted by this u bracket indexed by b, is called the coordinate vector of u with respect to curly b. Okay, so the coefficients of the linear combinations of v1 up to vk is called, or are called, the coordinates of that vector with respect to that basis. Okay, let's do some examples here. We have a vector -1, 2, 1, and the basis here is 1, 0, 0, 0, 1, 0, 0, 0, 1. Well, remember that these vectors are E1, E2, E3. These are the standard orthogonal vectors in R3. And while it's obvious what to do here, in this case, -1, 2, 1 is equal to -1 times E1 plus 2 times E2 plus 1 times E3. So the coefficient of E1 is C1, coefficient of E2 is C2, coefficient of E3 is C3. There's only one way to write this, and those are these guys. And then the vector, so let me call this guy u. U in this basis can be written as -1, the coefficient of first vector in the basis, then 2 and 1. As you can see, in this case, actually we are getting exactly same vector that we started with. And this is in general true. In general, the coordinate vector of u, which is, well, let's say x1 up to xn in Rn with respect to the basis E1 up to En is the vector u itself. Meaning that u in that basis, the coordinate vector is going to be exactly same thing, x1 up to xn. And the reason for that is that u is equal to x1, e1, x2, e2 up to xn, en. Well, if you change the basis, then these coordinate vector and coordinates will change. You see this u, I'm having the same u in the second example, but the basis, instead of having standard orthogonal vectors, I'm going to use this basis 1 0 0 1 1 0 1 1 1. Okay, so to see what is the coefficients of these vectors which give us u, we have to solve this system. Yes, 1 1 0, then 1 1 1, augmented negative 1 2 1. And well, this is a row echelon form and you can solve it right away. The coefficient, let's say this is C3, this is C2, this is C1. C3 is equal to 1, C2 is equal to 2 minus C3, which is 2 minus 1 is 1. C1 is negative 1 minus C2 minus C3, which is negative 3. This means what? This means that u in this new basis is given as negative 3 times 1 0 0 plus 1 times 1 1 0 plus 1 times 1 1 1. Okay, and well, this vector u, the coordinate vector of vector u in the basis a, is not going to be again negative 1 2 1. This is going to be negative 3 1 1. Let's do one more example. Here I have 1 1 0 and the basis is 1 2 1 negative 1 negative 5 negative 2. So we need to check to see how this matrix, this vector can be written as linear combinations of these two. Okay, we need to solve this. So row 2 minus 2 row 1. This gives us 0 here. This will give us negative 5. This is negative 1. And this is 1 and negative 1. How about this one? So R3 minus R1. Yes. So this will be 0. Negative 1 plus negative 2 plus 1. And this will be negative 1. And 0 minus 1 negative. The first row stays the same, and then well we can get rid of these two guys, and that's just R1 plus R2 R3 so maybe both of them minus R2 minus R2. So in this case this will stay the same. Subtract those guys, this will be 0, this will be 0, but this will be 2. And solve this. This means that C2 is 1. Negative C2 is negative 1 means that C2 is 1. And C1 is 2. In other words, 1 1 0 is 2 times 1 2 1 plus 1 times negative 1 negative 5 negative 2, and 1 1 0 in the basis beta is going to have this coordinate vector 2 1. It would be better if I had a name for this. Let me write V, and let me write this guy. The coordinate vector of V with respect to basis B is going to be 2 1. There are only 2 elements in the basis, so the coordinate vector is going to have only 2 components. Okay. So that's what the coordinates of a vector in a basis mean.